On the screen, I have these 4 shapes, and I'll give you a quick story about each one of these shapes very quickly, and then I'll explain an aspect of machine learning behind these shapes. The first shape is very simply a line. So for example, if imagine depressingly somewhat, if you're trying to buy a house in the Bay Area, and you make a plot of the price of the house versus the square footage, you will see a linear relationship. And in machine learning, this is called a regression problem, where imagine if somebody said, I want you to predict the house price, I'll give you the square footage. You might draw a line through the set of points that you've collected, and that might give you some sense for how much you'll end up paying for the house. And obviously, you'll decide you can't pay for it. But nonetheless, that's the process you'll go through. So I want to give you some insight into how does this machine learning process work. What does regression do? Regression assumes that your data looks like a line or a plane, and then it tries to find the best line or plane that looks like your data. Okay, so keep that verbiage in mind. Another common problem that we solve in many different contexts in business or in science is called clustering, where you're given a bunch of data and you're trying to determine, are there self-similar parts of the data? So for example, if you've collected data about, let's say, a lot of patients who have diabetes, type 2 diabetes, let's say, you might want to know, are all type 2 diabetes patients similar, or are there multiple types of type 2 diabetes patients? So you might attempt to solve it via a clustering problem. And the way clustering works is, again, very similar to regression in that you assume that your data breaks up into multiple pieces, and then you try and find the best decomposition of your data into that many number of pieces. Right? So similar to regression, you assume a particular shape, and then you try and look for that shape in your data. The third example is a loop. Imagine that you are an economist, and for every year you figure out the interest rate of the Fed and the growth rate of the economy. And these are your 2 axes, and you put a dot for every year that you collect the data. You will notice that the data evolves in these cyclic patterns, where when the interest rates are low, economies grow, and then eventually when the economies have grown too much, the interest rates are tightened and the economies start to shrink again. Again, we are in topsy-turvy world these days, so no bearing to real world these days, apparently. But nonetheless, that's what you would see in your data. I'll come back to that picture in a second. Look at the fourth picture. Imagine that you're, let's say, flying from San Francisco to New York, and you stick 2 sensors on the plane. You measure the amount of lift that the plane is experiencing versus the drag that the plane is experiencing. And when you plot the picture on the screen, you'll see a picture like this fourth picture on the screen here, which is that for the most of the flight, you will be in the middle part of the region, where lift and drag change a little, but not a whole lot. But there's a few anomalous things that happen. You take off at some point, you land at some point, and you might go into turbulence and come back at some point. And those are the 3 flares that you see here. Okay. Now with this background, I want to make 2 points. The first point is that the shape of the data actually contains a lot of information about it. If you knew the shape of the data, you wouldn't have to ask many questions about it going in. The second is, we have great algorithms called regression and clustering that solve the first 2 problems, but we don't have an algorithm called loop detect or flare detect. And in fact, the category of shapes that you actually see exhibited in real data sets is so vast that it's kind of pointless to come up with a prototypical shape first and then look for the shape in the data. And so that is kind of the motivation behind using topology to understand the shape of the data, because the shape of the data is meaningful. Everybody with me thus far? Yeah? All right then. So for people, I'll go through this slide very quickly. This is for people who might be slightly more technical in the machine learning space. But I just wanted to give you a sense of sort of how this interacts with machine learning, or how it's dependent on machine learning. So what you see in this picture, there are 3 data sets. Every row represents a data set. So the first data set are these kind of 2 clasping points. Half the points are blue and the other half are red. The shape in the middle has blue points in the middle, and then there's the circle of red points that envelopes that. And then the third shape is basically 2 clusters, red points here and blue points here, kind of like politics, I guess. So And what you see in every column thereafter is a particular machine learning algorithm trying to discriminate between the blue points and the red points. Okay? So you see the decision surface of these machine learning algorithms. The exact names of these algorithms aren't important, so don't worry about those. What's important here is that you can see two things. The first thing is that data has shape, as you can see immediately in this toy example. The second thing you can also see is that every algorithm also has a shape. So for example, if you look at the second column, which is the first colored sort of picture with the bands, you will notice that no matter what the shape of the data is, the algorithm always has this linear structure where it will find a line and then it will discriminate away from it. If you look at the second from the last column, you will see that this algorithm has a shape which is that it wants to discriminate data into boxes. So it wants to find axis-aligned boxes that have various opacities. And so the key realization here is that data has shape and algorithms also have shape, the algorithms that we use currently in machine learning. So it is really important for us, if you're going to have a hope to understand what's going on in these algorithms and how they make decisions, it's really important for us to understand how these two things are linked together, how the algorithms work together with the shape of the data, and when will they make errors, and what kind of errors will they make. Everybody with me thus far? So just quick summary, and then I'll switch into examples, which will be a lot more fun. Topological data analysis is basically a formalization using this old area of math called topology that allows us to study shape of data, shape of algorithms, shape of decision surfaces. For people who are slightly more technical in the audience, it allows us to merge together the results of various other algorithms in a coherent way that you can learn from it together. And the final point that's the most interesting point is that it's a compressed representation. It compresses the data. And compression is really important, because when people talk about big data sets and how vast it is, big data sets are actually kind of useless. You want data sets that are as small as possible. You want to eliminate complexity that's meaningless, right? So if you go back to the thing that I said about the map, there's a lot of complexity in that map. The exact shape of the coast is kind of irrelevant. So there are many, many details in data that are irrelevant, and it's actually very useful to understand the essential complexity of the data. So compression is a very key part of all sorts of machine learning, and in particular, topological data analysis is kind of based on outputting a compressed representation. And it also happens to be visualizable, which is sort of very, very, very useful.